All right, physics class, let's take a look at this work and energy worksheet, kind of get ourselves back into the swing of things. So, we had talked about work and energy before break, but let's just get back at it here. So work is done on something when a force is applied and results in that object being displaced a certain distance. So force and a distance. So you got to have the force moving the object to actually have their work being done. All right, so that work could do a couple things. It could cause the kinetic energy of the object to increase, a certain number of joules. It could cause the object to increase its potential energy via, be it a gravitational potential energy or spring potential energy. It could also cause it to dissipate energy in terms of friction, applying a force and taking away kinetic energy. So we're going to look at some of these different examples here and get started on this worksheet. So in all of these problems, we're going to assume a constant force, all right, or an average force if we don't know exactly if it's constant or not. Also, technically speaking, the force only does work if it's parallel to the object's displacement. So these problems, I need to restructure them a little bit. I have a mistake here. This should be -10. I need to fix the original master file there a little bit, but we'll go with it as I gave it to you here. So determine the amount of work done on the block initially at rest by a positive 10 Newton force applied over a distance of 2 meters. So this object starts at rest, v initial 0, and then the velocity ends up being big by the end. So this force is going to cause an increase in kinetic energy as this object moves over this distance. So the work done here is going to be the force times the displacement. All right, so the force here is positive 10 newtons. The displacement is positive 2.0 meters. So the work done is positive 20 Newton meters. All right, positive 20 Newton meters of work. So what would have to happen to the block's speed and its kinetic energy as the force is applied? So we've learned so far that kinetic energy is related to speed. As the speed increases, kinetic energy goes up. As the speed decreases, that means the kinetic energy is going down. So what would have to happen to this block's speed? Well, it has to go up because it starts at rest, it has a force being applied to it, it's going to accelerate. We already know Newton's second law, right? A force accelerated to an object, unbalanced, it's going to cause it to accelerate. Therefore, its velocity is going to increase, its speed is going to increase, it's going to have an increase in kinetic energy. All right, let me lock my focus here. Sorry about that. All right, so speed must increase. A equals F over m, right? Newton's second law. It's accelerating because there's a force. And therefore, remember that old symbol, therefore, KE must also increase. Okay? So we saw positive work. We saw kinetic energy increasing. That's an important thing to note, and we'll see that in a minute. So determine the amount of work done on a block initially moving at positive 10 meters per second by a negative 10 Newton force. So the object's moving to the right and the force is to the left. All right? So already you should be kind of picturing V is going to have to go down, right? It's going to have to reduce in size because the force is to the right, the force is to the left, the initial motion's to the right. So this is like you give something a push and it slows down and stops. The motion is to the right of the screen, but the force is to the left, so it stops. All right, so let's find the work done. So work equals force times displacement. Force in this case is negative 10 newtons. The displacement's still positive 2.0 meters. All right? It's starting off with velocity, or starting off with kinetic energy, and then losing it. So the work done here is negative 20 Newton meters. Okay, so what happens to the block's speed and kinetic energy as the force is applied? They must decrease, right? They have to slow down. The block, must slow down. My writing is a little bit off today. I haven't written in a couple weeks very much. Block must slow down. Therefore, KE must decrease. KE must decrease. So, we see the work is negative, the kinetic energy goes down. The work is positive, the kinetic energy goes up. All right. So we got to pause for a second and talk a little bit about that unit we've been doing, Newton meter. You may remember a Newton meter, a Newton. So a Newton is a kilogram times a meter per second squared. So if you multiply it by a meter, you get this unit here, Newton meter. We call that a joule, capital J, named after this guy, James Joule. All right, so you can read the biography information here, kind of interesting. Yeah, so let's move on to number 3 here. Interpret the following statement. If the applied force is pointing in the same direction as the displacement, the work done is positive. If the applied force is pointing in the opposite direction of the displacement, the work done on the object is negative. So if something's moving, right? So if I give this thing a push and it displaces to the right, the kinetic energy's got to go up. If it's displacing to the right and the force is against the motion, it has to slow down. All right? So what does work being positive or negative mean? Well, if work is positive, positive work means increase in KE. Negative work means decrease in KE. Positive work is an increase in kinetic energy, negative work, decrease in kinetic energy. All right, we saw that on the first page here. So let's see what we get here. Wooden block starts from rest and a constant force of 1 Newton pulls the block to the right against a negative 0.7 Newton frictional force. Draw a diagram of the situation including forces acting. All right, so we're tying it all together here, right? We got forces, we've got motion, we've got energy. It's all coming together. This is physics, right? We got one more thing to add to this, which is going to be momentum. And then we're going to have all of mechanics kind of wrapped up into one thing. Anyhow, force diagram. Okay, so here we go. There's the object. It's the dot, right? The dot represents the wooden block on the desk. I put it on an axis for a coordinate system. All right. I'm going to have the applied force here. I'm going to draw that arrow kind of like that. So this should be review. This is positive 1.0 Newton force pulling that way. We got a frictional force here going the other way. Not quite as big. I didn't do a very good job here drawing that. Force to the right should be a little bigger here. This is negative 0.70 newtons. And of course we have a normal force and gravity, which are going to balance each other out. All right, so 4 forces acting on this object, Fn and Fg, they don't really matter. They balance each other out. These are the 2 forces that are interesting, right? So this is kind of going back to the Newton's second law where we had a pulling force, a resistive force. All right, F net here would be positive 3 newtons. You may remember that. Positive 0.3 newtons, right? So it's accelerating to the right because, I can draw an arrow here to represent the direction of acceleration. Acceleration's got to be the right because the force pulling to the right's a little bit bigger. Let's see what it's going to ask us, though, on the next page. It says determine the work done on the block by the applied force after 2 meters of pulling. Okay, well, the work done by the applied force here is going to be the applied force multiplied by the displacement. So if the applied force, right, is positive 1.0 newtons, the distance is positive 2.0 meters, So that is the work by the applied force. I'll call it work FA. We'll call that the applied force. FA is going to be positive 2.0 joules, which is Newton meter, joules. So the applied force is trying to increase the kinetic energy by 2.0 joules. All right, work done by friction now. Force of friction equals the force of friction times the displacement. So the force of friction is negative 0.70 newtons times positive 2.0 meters. All right. That ends up being, work of the force of friction ends up being negative 1.4 joules. All right, so friction, while the applied force is doing work to increase the kinetic energy, friction is robbing kinetic energy from the block, converting it into heat energy or thermal energy, and the block can't get up to as great of a speed. So determine the net work done on the block. All right, well, work net would simply be the sum of the works, right? It would just be add these together. It'd be plus 2.0 joules minus 1.4 joules. The net work being done here is positive 0.60 joules. That's the difference between these two. The net force acting on the block, F net, well, that would be what I talked about on the previous page. It'd be positive 1.0 newtons minus 0.70 newtons. That'd be 0.30 newtons. All right, and look, work net also could be solved by doing F net times the displacement. So that'd be 0.3 newtons times 2 meters, 0.6 joules. So those are just some basic work calculations. We're going to see on the next few pages here, like questions number 7, 8, and 9, which we're going to get to 7 through 11, I should say. It's going to be a little more quantitative, but I do want to introduce something right now. I might do this in a, I'm going to do this part in a separate video, okay? The derivation of these formulas here. So let me stop this and then I'll start another video.